problem so far?
No, sir.
No, sir.
Okay. All right. We're gonna start our session or our lesson. So now, as I mentioned just now, we in week 9. So this week, the topic is the introduction to alternating current. And right, what we're gonna learn, the outcome of this session. We try to understand sinusoids. Do you know what is sinusoid? Do you
No.
have any idea what does it mean by sinusoids?
No.
No,
No.
you didn't do the revision that I told you earlier, I believe. Uh, okay, never mind. Um, Sinusoid and phasor properties. We try to convert from time domain, either voltage or current, into a phasor domain, or sometimes called as frequency domain. Time domain to frequency domain, or time domain to phasor domain, it's the same. And then how do we graphically represent the vectors in frequency domain? Vectors, I mean voltage and current. And then we try to calculate impedance. Okay, this is something new. Previously, you get to know components like resistor, and resistor will represent you a resistance in a circuit. Now, in frequency domain, especially, or in phasor domain, we have three components over here. We have resistor, inductor, and also capacitor. The combination of those three elements, or three components, will be called as impedance. So now you're going to calculate what is the value of impedance, and maybe later on you will find out that, okay, impedance is basically the combination of two quantities named as resistance and reactance. The reactance part is something which I consider new for you guys. All right, here is this, as I described earlier. At the end of the lesson, we're gonna have a homework. I think 5 questions. If you look at the file that I uploaded in e-learning. Okay, now previously, okay, these two topics, frequency response and filter, was taught in this course. Since we do some modification workshop to improve our course, so we decided these two topic is neglected or being removed from this course. Means that we're going to talk a lot in AC circuit analysis in terms of the analysis itself, as well as the power in AC circuit. So previously we do have these two topics, and I believe these two topics is more challenging compared to what we have now. What we have now is we try to focus more on analysis, AC circuit analysis. Then we recall back the thing that we learned over here, circuit law analysis, to be applied in order for us to analyze the circuit. And furthermore, we will introduce you guys with AC powers. If you remember, in DC circuit, we do also calculate the powers, like power dissipated at resistor A, resistor B, something like that, or power dissipated in the circuit, a DC circuit. And the power involved in DC circuit only associate with components which called resistors. However, in AC circuit, before that, associate to resistor, and the unit of power in DC circuit is watt, if you remember. And for AC circuit, we expand the knowledge on power itself, where power can be where power is consist of the combination of three elements, or comes from three elements, and it is not called power anymore. It's called power, but been divided into three. First, due to resistor, yes, it's the unit is watt. The first one, the second one is for component like resistor and like inductor and capacitor, which is called as reactive power, and the power caused by resistor is called as active power, and the other one, which is caused by inductor and capacitor, is called reactive power. So this is something new in terms of the knowledge or the content in AC circuit analysis. So that's what you will expect in AC circuit analysis. And if you remember, yesterday I did post you guys, or I did share, ask you guys to have a look at the video that I sent or posted in e-learning. And I have a question here. In your opinion, what is the main advantage of AC compared to DC? If you look at the video, can anyone respond to that? Can you hear me?
Is a big.
Huh?
Wait. Macam mana dia cakap?
You don't have to spend another 15 minutes to look at it. I believe you already spent your 15 minutes yesterday.
Yes. Sebenarnya yesterday.
Okay,
before.
yeah, trying.
Yes.
So this is like opinion question, not necessarily stated in the video. Maybe based on your observation from the video. Oh, this is why people use AC.
Maybe because, sir, it's AC is mainly used for high voltages, like from power stations, and they can reduce it easily for like safer use.
Safer use.
Yeah.
The one that you mentioned just now, power station, high voltage. Yeah, it's related to that, but I'm looking for one keyword here. Can you relate that information? High voltage, power station.
I think because it's AC is alternating current, which we can alternate ourselves.
Yeah.
It's easier for us to convert AC electricity than it is for us to alternate DC.
I prefer the one that you explained earlier, because the one that you explained earlier is more related to the real answer that I'm looking. Okay, one of your member here says that efficiency. Yeah, related to that. Okay, it's okay. You can have a look at it, because we don't have to spend much time on this. just an opinion, right? Um, if you look at the the video, maybe it describe about um, the transmission of power, okay, using AC. It's less expensive compared to DC. Yeah, have you come across with that one? People
Uh,
people
I've only heard it's safer.
safer. Yeah, okay, safer. But in terms of okay, safer in terms of domestic use, I think.
Yeah.
But if you look at the main advantage, basically it's due to the transmission cost. If you like to transmit power, okay, DC power, last time during the war between Edison and Tesla, they tried to transmit powers. Right? Edison tried to transmit power or transmit voltage and current. Tesla also tried to do that, but what happened is that for DC, it can only transmit power up until 2 kilometer radius. And if you need to transmit further than that, you need to have more voltages. Maybe you need to set up another power station near to that one. And for lighting a bulb, maybe around 2 kilometers radius uh, is possible. And for AC, since you can step up your voltage, you can transmit your power a lot more further. Means that the introduction of a transformer able make the power transmission to be able to transmit in a long distance. So that's the main advantage of AC. And related to that is cost. So transmitting AC power is less expensive compared to DC. So that's I think for me lah. In my opinion, I think it's due to the cost of transmission, and the one that you explained to me just now about power station. Yes, of course, it's related to power station. And what else? High voltage. Yes, of course. We try to transmit voltage. We try to transmit power by stepping up our voltage, and by stepping up our voltage, the current will be reduced, and the loss of transmission loss will be reduced as well, because we know that transmission loss is related to the equation of I squared R. So you need to boost your voltage in order for you to try to reduce the current you are transmitting. And later on at the other end, you try to use transformer back to step down your voltage and uh, get the current that you need. So that's, I think, the advantage. Maybe this is something which is a general knowledge for you guys, but as electronics engineer, you should know what is the main advantage, because this is something like basic argument or basic not argument lah, basic knowledge for you guys to know. Anyway, that's I don't know. Maybe it's in the video. Maybe you can find other video that explaining the maybe the significant advantage of AC compared to DC. All right, safety. Yeah, I also agree with you. All right. Now we move on to our next slide, which is sinusoid. Have you come across with this kind of waveform?
Sinusoid waveform.
Yeah, yeah. This is the waveform of AC current, AC voltage. If you look here, tell us that there are a number of natural phenomena that is sinusoid in nature. Yeah, of course, oscillation, something like that. A sinusoid is a signal that form of sine and cosine function. The sinusoid is a oscillation kind of waveform, can be represented in sine or cosine function. If you look at the sinusoid itself, basically this is what you expect in AC current or AC voltage. And the characteristic that we have here is that it's relate with the value of this highest value over here is called peak value. And the cycle over this is one cycle. And if you have this one cycle of period, it will relate to the terms called frequency. So that frequency can be changed if the period over here change. Okay, I want to ask you guys, if you, I don't know, maybe in your country, maybe in Qatar, in Bangladesh, maybe the frequency it's different. I want to ask common frequency applied in United States. Okay, what is the frequency of voltage? If you look at United States power outlet, what is the frequency they are using out there? Anyone?
Again?
What is the frequency of voltage system in United States, America?
What is the what, sir?
Okay, again, the question is, what is the frequency, voltage frequency used in United States of America?
Is that a general question, sir?
Yes.
The 60 hertz or 50 hertz?
Yeah, right. It's 60 Hz. 60 Hz. Normally US based country, or I don't like to call US based, US standards. They tend to use 60 Hz as their voltage or current frequency, outlet frequency, voltage outlet frequency. And for UK standards, for those for countries which is using which are using UK standards, for example Malaysia, we are using 50 hertz voltage or 50 hertz power outlet. So that one just general knowledge for you guys. Okay, we move on. A lot of storytelling today. Right. If you look at sinusoid, the waveform itself, this is the way we write our sinusoid voltage or sinusoid waveform, sinusoid voltage, current, and so on. We have V of t, so the voltage itself varies in time, respect to time. And we have Vm over here, which is the peak value. Vm means V maximum, or sometimes Vp, V peak. This is the peak value or maximum value of the sinusoid amplitude. Sine, okay, sine is the trigonometry parameter operator. Sine omega t. So there are two things that you need to really understand over here. We have voltage, which is represented by peak value, but in the waveform characteristic itself, it varies with respect to time. Sometimes we're gonna have a positive peak value. Sometimes we're gonna have a negative peak value. but this is the peak value of it. For example, if you have like here, we have Vm here equals to 10. So we do have some, a value over here, down here is about negative 10 volts, for example. And here, the second one is about this omega. Omega is known as the angular frequency, and information that we will get from this omega is the frequency itself. Frequency, the period, and it's related, or it can be written using this equation. T, or the period, is equals to 2 pi over omega. In other words, if what is omega? Omega is 2 pi over t, or omega equals to 2 pi f. This is a standard equation for omega. Omega equals to 2 pi f. Please remember that. Okay. And as I mentioned earlier, omega equals to 2 pi f, or we can write it as omega equals to 2 pi over t. So here we found that the period and the frequency is inversely related. So now if you know what is your period, and you can easily calculate your frequency by using f equals to 1 over t. And one more important thing is that frequency, the unit of frequency, okay, is called hertz. So frequency units is hertz, and the period, okay, units is called second, per second. And the units of angular frequency is radian per second. Okay, a little bit on more on sinusoid. More generally, we need to consider the relative timing of one wave versus another. So in your course, you will given, for example, you will given two waveform sinusoids, and you try to compare the phase shift between two sinusoids. So that's what you're gonna expect in your course. For example, here we consider two sinusoids. We have V1, okay, V1, yeah, the one we have here, and V2 is the dotted line over here that you find over here. And if you see here, both sinusoids is shifted, if do have a phase shift between each other. And the way we write the first one, or V1, is like V1 equals V1 of t equals to Vm sine omega t, because it starts from omega equal to 0 over here. If you look at V2, if V2, we have a phase shift, a bit of phase shift over here. V2 can be written as V2 equals to Vm sine omega t plus, okay, plus this phi is the phase shift of the waveform. Okay, this is the phase shift due to this angle. And if you try to compare, okay, here we can compare these two waveforms, and we found that V1, V2, sorry for that, V2 leads V1 by this angle. I should use green, by this angle. And if you get the opposite, or get V2 as your reference, you can say that V1 is lagging V2 or lags V2 by this pi degree. Right. This is very important because you will find it quite often in your in this course. So this is what you call it the reference. If you keep V1F as your reference, okay, this is the reference, your reference, you can say that, okay, V2 is leading V1 because V2 appears earlier than V1. And if you regard this waveform as your reference, you would say that V1 is lagging V2 by the angle here, the phase shift angle. So this one, you can say that V2 is our reference. And this statement is based to sinusoid. You will find this kind of what do you call it? We will try to ask you guys what is the characteristic, whether it's leading or lagging, something like that. So you need to write your answer based on this kind of statement. All right. This is something that I don't like to get into details because it's mathematics. Sinusoid may be expressed as sine and cosine, you know that. And we can transform the sinusoid of sine to cosine or vice versa from this trigonometry relationship. So you need to remember all this, but I believe for you guys, you don't have any problem to remember because the exam will be in terms of online mode. So you have plenty of time. I mean, you have the opportunity to have a look at the trigonometry relationship. However, you still need to do revision in terms of how to use these relationships. And of course, we go a bit the definition in terms of AC circuit. You will come across with terms called phasor. What does it mean by phasor? Here it says that a phasor is a complex number, okay, that represent amplitude and phase of the sinusoids. Therefore, basic knowledge on complex number theory is essential. If you look at earlier that we have over here, oh no, not here, supposed to be here. Okay, this is considered, okay, the voltage here, or maybe not here, maybe I try to use this slide. Okay, this kind of arrangement, okay, this kind of equation is considered as in time domain. Because we do have this time influence over here and also over here as well. The phasor that you see in the next few slides is we try to write this time domain equation into, we try to represent it in terms of amplitude and also the phase. I mean, amplitude and angle of the sinusoids. And here, conversion, or when we try to convert from time domain into a phasor domain, the phasor will be very important for us to, in order for us to get to know what's going on actually in how does the equation transform, and why do you need to transform itself. to transform the time domain into a phasor domain. So here, this is introduction of phasor. Phasor means that we try to convert the time domain into something which is known as complex number and can be represented in amplitude and phase. Phase means this is angle actually. Angle. And complex number can be represented, this is known as rectangular form, and also can be represented as this equation known as in polar or exponential form. But in your course, we always look at this kind of equation, consists of amplitude and also the angle or the magnitude and also the angle of your time domain voltage or time domain current expression. This is less significant at the moment in your course. But maybe if you, in your year 2, year 3, maybe you will come across with this. Maybe in maths subject, you will come across with this kind of exponential form of complex number. Okay, remember, complex number, phasor can be represented by complex number, and complex number can be represented by these two forms. First one is called rectangular, the second one is called polar form. Okay, and this is something which is revision to complex number, but you can also find it in other maybe source like YouTube, something like that. In mathematics book also available. Okay, what does it mean by complex number, and how do we interconvert it? So like, how do we convert from rectangular form to polar form and polar form to rectangular form? So this is what we have if you try to calculate it manually. And if you have rectangular form and you try to convert it into polar form, okay, what you need to do is you, for example, rectangular form, we have that A equals to M, sorry, not M. Here is X and Y. X plus minus something J Y. Okay, maybe this is something new. What does it mean by this J? Okay, in mathematics, normally they will write like this: X equals to, not X equals, sorry. Okay, A equals to X plus minus I Y. Okay, and the one that you see over here, J and I, basically describing the same thing. It's describing the imaginary part. Imaginary. Okay, so that's why we have imaginary axis here, we have real axis over here, and this X is basically the real part or the the real axis value. And if you have this form of complex number or rectangular form of your complex number, you can convert into a polar form, where polar form, what we need to have is we need to have the radius or the line you see over here, the diagonal line. So this diagonal line, or this something this is sometimes called radius, can be calculated using this equation: x squared, the value of x over here, squared plus value y squared, and we square root it back. And the angle, because we need to write our polar form, like E equals to R with angle 5 over here. Okay, this is the angle. So R value can be found using this equation, and the phi, or the phase over here, can be found using this trigonometry relationship, where you will use arctangent 1, arctangent y divided by x. And if you have a polar form, you can always convert it also into a rectangular form. If you try to convert into rectangular, you will use this equation and also this equation for x and y respectively. Okay, but nowadays, conversion is not a problem anymore. You don't have to use this kind of, maybe you will use this in mathematics course, but for electrical engineers, it's easy nowadays. Easy in the sense that, okay, if you look at call it polar to rectangular conversion. If you look at Google and you see this is the website that I'm talk about here. Okay, you try to convert from polar to rectangular using online calculator. It's quite easy. For example, you have rectangular to polar, and let's say your real part is 10, okay, and your imaginary part also 10, and you calculate. It will straight away give you the answer. What is the R value? R is over here, and the phase value is over here. It's very easy. So, and also in your calculator, if you have advanced calculator, maybe mine is not that advanced. Maybe mine is just old version of Casio scientific calculator. Maybe you have latest version or maybe advanced version of Casio calculator. You can easily convert from rectangular to polar by using the tools or your calculator. And maybe if you have internet connection, you can use this website as well. So it's not a problem anymore, this mathematics stuff. Maybe, sorry about that, maybe during my time, or maybe during your time in mathematics course, you need to really know how to calculate the conversion, how to do the conversion manually. Okay, but in my course, in this course, I don't mind whether you try to use your calculator or you try to use a website. I have other important things that I would like to ask you guys rather than this kind of basic mathematics. So that's why I think for engineers, mathematics is should be in your fingertips lah. You should know how to calculate any kind of problem. If you try to convert from rectangular to polar, or maybe you try to do differentiation, integration, it should be within your fingertips. And within your fingertips, maybe you can find sources, like you can find websites, maybe you can find tools for you guys to solve the mathematics problem. But the main problem is how do you look at the circuit? How do you translate the circuit? What is the important, the connection itself? How do you relate that one and use mathematics to solve your circuit? Okay, anyway. All right, if you look at the one that we seen earlier, we are talking about complex number, and in complex number, it also we should also obey the mathematical operation. So this something which is very crucial, because if look here, if you want to add two complex number, you need to add two complex number in rectangular form. And same goes to subtraction. You need to subtract. If you try to subtract two complex number, you need to use a rectangular form. However, for multiplication, you can simply use polar form to multiply two complex number. There's a lot more over here up until complex conjugate. So hopefully you do some math revision over here. However, I think your calculator can easily add, subtract, maybe multiply, divide easily using whether you have rectangular form or whether you are in polar form. So you don't need to really what do you call it, convert. If you, for example, if you like to do addition, now in your question you have complex number in polar form. So if you try to add those two complex number, you need to convert first. But I think your calculator easily can do that, although you are in polar form. Okay. If you remember, maybe this is something new, Euler identity. You can also represent your phasor in Euler representation or Euler identity, which is written using this equation. But in this course, this is less important, because maybe it's important in mathematics course, but in this course we try to use polar and rectangular form in order for us to analyze our problem or our circuit. So this is continuation for what we have seen earlier based on Euler representation. However, what is significant here is that if you see here, this is a time domain representation of our voltage, and this is a phasor domain representation. And this phasor domain, if you look here, is our complex number here is represented in polar form. And please remember, this polar form also can be written or can be converted into a rectangular form. So rectangular and also polar form is basically falls into phasor domain representation. And for time domain representation, you see that we have time involved in our equation. And if you try to represent this voltage in time domain or in phasor domain in graphical representation, so this is how it looks like. But I think this one is a bit difficult to understand compared to what I will teach you guys later on. Maybe it's easier. Maybe we will leave this one first. Later on, I will tell you guys the easier way in order for us to have a graphical representation of our voltage or our current. All right, here it's a table where we try to transform from or we try to convert from time domain to phasor domain. So for example, here we have Vm cos omega t plus phi. So we can write in phasor domain as Vm with the angle of phi over here. And if this is considered as our reference, the reference here is cos. So if you want to write the voltage in sine waveform. So you need to minus this angle 90 degrees. Same goes here. Here is also the same. See here, we consider this one is a reference. Okay. Basically, you can set your reference as cos or sine. However, in this table, cos have been set as the reference. So if cos voltage written in cos sinusoid over here is our reference. So if you try to write in sine as sine waveform, you need to add the negative 90 or you need to minus 90 degrees. Same goes here. I have current written in cos. This is considered the reference. And you should write, if you want to write in sine, so it will become omega t plus phi over here. And you need to add negative 90 in the phasor domain representation. Okay. Maybe we skip this one. You can write. Okay, this is what I said earlier about try to graphically represent your voltage or your current equation in graphical representation. So, for example, if we have like here we have Vm with angle of phi. What you need to do is you need to draw this line. This line is the magnitude of this Vm. Okay. For example, this Vm is 10. The angle here is like, let's say 45. 45. So what is 10? 10 is drawn over here, the length of this line, and 45 is the angle over here. Okay. So this is a graphical representation of your voltage over here. And let's say we have another one. We have Im angle of negative theta. Okay. And let's say the value here is like we have also 10. And the angle here is negative 30, for example, yeah? So what is 10? 10 is the length over here, length of this line. Oops. This is 10. And negative 30 is the angle from real axis towards clockwise direction. Okay, this is negative 30. If you look at your Argand diagram, this is known as Argand diagram. Okay. From here, positive angle. From here up until here, still this is a positive angle. And from here to here is a negative angle. We consider that one is a negative angle. And if you look at, for example, if I have angle of 200 degree, okay, for example, let's say my current is I with the angle of 200 over here. How do I draw it? Okay. Here we have a positive value of our angle. So the way we draw it is like this. Okay, I with the angle of 200, I would draw it like this. Um, 0, 90, 180, this is where my eye is. Then the 200 degrees is drawn like this. This is the 200. Theta, theta equals 200. Okay. I can also draw this vector, okay, like this, because this is this vector or this complex number can also be written as this. I with the angle of what? 200 over here. And what is the balance here? 180, 200. So this is negative 160. So I can also draw the same vector and consider the angle is from the negative side. So this angle is considered as negative 160 degrees. So it doesn't matter. If what you need to remember is that if you consider this one is a positive value, means that you need to do it counterclockwise. If the angle is a negative value, and for example like this, you need to start from the origin or the angle 0 up until following the clockwise direction and up until the angle that you desire. So this is how we draw, how do we represent our vector in graphical representation. This is something which is useful for you in order to analyze which one is leading, which one is lagging. For example, let's say here we have okay, let's say we consider this is the one that we try to analyze. For example, here we have VM, this angle over here, and let's say this is, sorry, not 30 degrees, 45 degrees. Let's say this is 45 degrees, and this is negative 30 degrees. If I want to write the relationship between voltage and current over here, let's say I V as my reference. V as my reference. So let's say number 1, V as reference. Okay. I would say, I would write my relationship between V and I as I, okay, lag, wait, no, okay, I lag V by, okay, 30 plus 45 by 75 degrees. Okay, this is how I write the relationship between voltage and currents we see over here. And if I consider, number 2, if I consider I is my reference, I as reference, okay, I would say that V lead I, okay, also by 75 degrees. 75 is coming from combination of these two angles. So this is how we write. That's why I said earlier, the this one, this definition or the way we write the relationship between current and voltage is very important, because we need to analyze whether which one is leading, which one is lagging. It's always being asked in your assessment, whether in test 2 or in your final. It will be asked. Okay, right. That's for phasor diagram representation. Maybe we're gonna have a look at it later on in tomorrow's session. Okay, now we move on into examples 9.1, 9.2, and 9.4. 9.1 is very easy example. You need to find the amplitude, phase, period, and frequency of sinusoid. Based on the information that we have over here, we know that this is related to the amplitude. Okay, if you try to look at the phase, this is related to the phase, the angle itself. If you would like to assess the period and the frequency, this is the thing that you will look into. So the amplitude, maybe this is rate based on this element, 12. So the amplitude here, Vm is 12. The phase related to the angle you've seen over here. The period and the frequency is based on this information. This is omega basically, omega. And omega in this case is 50. You will use this equation, omega equals to 2 pi f, or omega equals to 2 pi over t to solve the period and also the frequency. So this is the tip compared with general sinusoid function. And for second one is example 9.2. So here calculate the phase angle between V1 and V2. Okay. State which sinusoid is leading. Okay. Now, if you look at the tips I wrote over here, express both sinusoid in the same form. This is very crucial. Remember the slide I showed earlier. Okay. I have Vm with the angle 45, Im with angle of negative 30. I didn't mention about whether it is cos or whether it is a sine function, because it's already in polar form. You cannot find whether it is cos or sine. However, if you are given with this kind of information or equation of V1, we have cos over here, equation of V2, and we have sine. You need to make these two equations in the same form. For example, if you consider this is your reference, okay, not reference, this is your maybe reference is the best word I can say over here. So it means that you need to convert this one into a cos. Convert this into a cos. And how do you convert it? By using the mathematics that I showed earlier, using this, where is it? Okay, using this relationship. Okay, and if you consider this one, okay, as your reference, and you might need to convert this cos into a sine function. And the way you convert, you need to have a look at the trigonometry identity and try to convert from cos to sine. And later on, you use phase difference or graphical approach to determine the nature of the sinusoid. After you convert, after you for example, let's say we make one example. Okay, let's say this is the reference that we desire. It means that V1 negative cos omega t plus 50 is taken as our reference. You try to compare these two, means that you need to convert this one or V2 in cos equation. So let's say V2 already been converted. What you need to do next is you need to make it in number 1, convert, V2, okay, Number 2, write in polar form. Okay. Then write these two in polar form. And later on, number 3, let's draw. Okay. Maybe I erase this first. Draw. I just wrote the keyword over here, and I will explain later on. Okay, the first, you need to convert this into cos. And after you convert, the equation might be slightly different from what you've seen over here, maybe plus 90 degrees. Like say 12 cos omega t minus 10 plus 10 plus 90 degrees. And you need to write both equation, both V1 and V2 in polar form. And later on, you need to draw the phasor diagram or graphical representation of this complex number. So maybe you consider something which is look like this lah. V1, or for example, not necessarily correct. V2. Okay. So this is what the strategy that we gonna look at. So there are 3 steps. Here I have put the tips. Maybe later on you can have a look at example 9.2. You can see how the conversions, and also maybe later on it's a bit different from what I explained over here, because when you try to state which sinusoid is leading, we try to find the answer. Maybe they don't, the solution itself don't have graphical representation, but I would really prefer a graphical representation in order to analyze which sinusoid is leading or lagging. Okay. I think I have the solution over here. Example plus examples. Example 9.2. Here, if we look at the example, method number 1, in order to compare V1 and V2, we must express them in the same form. This is very important. We express them in cosine form with positive amplitude. So you need to represent, you need to convert both basically, because the one that you see for V1 is a positive amplitude and negative amplitude. You need to put it in a positive amplitude as this. So this should be minus 180 degrees. This is conversion to convert a positive value of magnitude into a negative value of magnitude into a positive value of magnitude. And for V2, if you write in sine, in cos, I did mistake over in the previous slide. I said earlier that you need to plus 90 degrees, but basically you need to minus 90 degrees based on the definition of trigonometry identity. So now V2, if you try to convert into a cos, so you need to minus 90 over here. Maybe take here, you need to minus 90, influence of 90 degrees. Over here is influence of negative 90. And once you have these both, these two written in the same sinusoid form. So now we have cos over here, we also have cos over here. So the strategy that's been shown in the solution is like just comparing the phase difference like that. So for me, I think it's better if we extend a bit our strategy or our solution. For example, here we have V1. We have V1 should be if we are we try to write V1 in polar form, we will write like 10 with the angle of negative 130 degrees. and V2 with the angle of, amplitude of 12 and angle of minus 100 degrees. Okay, and from here, I try to graphically determine which one is leading, which one is lagging by draw the graphical representation of both waveform. So for V1, 10 with the angle of negative 30 degrees, 130 degrees. So it might be somewhere over here. Okay, this for V1. Let's say this is 1 minus 130. And for V2, it's slightly down here, but longer line. Okay, because the magnitude over here is 12. So it should be longer than V1, because V1 we have 10. And the angle from here to here, oh my goodness. This is what I don't like, using this one. So from here to let's say, oh, I cannot do that. Anyway, V2 with the angle of negative 130, 100. And looking at these two waveform, we can identify which one is leading and which one is lagging. Looking here, we say that V1, okay, V1 is lagging like V2 by angle difference you see over here. So the angle difference over here is 30 degrees. But the question asks about which sinusoid is leading. So if you want to write in lead form, so we can say that V2 lead V1 by 30 degrees. So here I have the confidence that this V2 is leading V1 by my graphical representation, not just by looking at the equation. Okay, I say that V2 is lead. But here you see here, the way they determine which one is lead, which one is lagging is by using the equation itself, and plus 30 degrees. This one should be something we need to modify our equation. However, if you look at my strategy, since I've already converted the waveform into one single same form. For example, here we have cosine waveform, positive cosine waveform. So I can straightforward write my waveform in polar form and draw the graphical or draw the vector in graphical form. And by this graphical representation, it's easier for me to know which one is lagging, which one is leading, since the question itself asking about lead. So I need to write V2 lead V1 by 30 degrees. But basically, both are the same. V1 lag V2 is the same, except that here it is written in lag form. So lag means that you cannot write V2 lags V1. In this kind of arrangement, it should be that V1 should lag V2 by this certain angle difference. Try to have a look at the second method later on, but I think both are the same. But here, the way they write down, or the way they represent the graphical representation is in terms of the axis over here is represented by cos omega t. The y-axis here is represented by sine omega t. I think this one is a bit difficult for me to understand, but it's always in your textbook if you try to really understand how to draw using this kind of arrangement. But from my experience, I think this kind of phasor diagram is easier for me to understand. I just try to remember what is the angle, and if it's positive, I should use the counterclockwise. If it's negative, should use this clockwise direction. And also, the difference is the difference between these two angles. Oh, sorry, these two vectors angles. Right. And 9.4. This I think easy because a lot more easier compared to what we've seen over here. Says here, for example, 9.4, you need to transform the sinusoid into phasor. So actually, we have done it earlier in example 9.2, based on my the strategy that I suggested just now. And again, if you try to transform this into sinusoid phasor, from sinusoid into phasor form, you need to convert. If the sinusoid is in cos, you need to convert in sine. And if you consider sine is your reference, but if you consider cos is your reference, according to the book that you have, I think Sadiku, Alexander Sadiku book accept cos as its reference. So here, if you see, if we have a cos equation over here, it not gonna be translated into sine. So it's remain as cos as the reference. So now it accept cos as the reference. So we have 6 cos omega 50t minus 40. Straightforward, just write, take the magnitude over here and also take the angle to write it in polar form. However, if you have sine in your question, based on the example written by Alexander Sadiku, okay, and sine over here need to convert into cos, okay, first, and later on from the cos equation, take the magnitude and put it as the amplitude of your polar form, and take the angle over here as the phase angle of polar form. I also wrote down here about the explanation of this example. I said here that textbook uses cosine as its reference sinusoid function based on Euler identity. Okay, the textbook use cosine as the reference. We can also use sine as your maybe here I miss y, your reference sinusoid function. For example, if you use sine, means that the first question over here need to convert into sine. And the second equation for number B over here, you have negative sine. You need to convert it into a positive value. Okay, I want to stop for a while because a postman is on my door, so I need to 5 minutes break.
What happened? Bro.
Postman. He's got a post.
What happened?
He's got a post. He's getting. He's going to the postman.
Oh. Man, I just want to go to sleep, man.
Oh, by the way, can someone send me the attendance form?
Oh yeah, I have that. I think it's in the group though.
It doesn't seem to be.
Oh, I don't know. I don't know. Where did the chat go? Yeah, okay. Nasif sent it.
Okay, thank you, Nasif.
Anytime.
Okay, sorry for the interruption. Are you still there?
Yes, sir.
Okay, sorry for the interruption because delivery guys recall me. Okay, anyway, I think we shall continue a bit. Right. We finished example 9.4. You can see the details in the textbook here. Right. Relationship between phasor relationship of four resistors. For example, if you have a circuit, okay, consists of only resistor in AC circuit consists only, sorry, consider you have AC circuit consists only resistor in your circuit. That's the way I would like to arrange it. And the relationship between voltage and current is stated like this. The voltage and current are in phase with each other. Okay, let me try to draw the circuit. For example, we have like voltage source over here. Okay, let's say voltage source here I have 10 with the angle of, let's say, 20. Okay. My voltage over here is written in polar form, and let's say I have this resistor value is also 10 ohm. And the question is that what is the current here? Okay, I can straightforward apply Ohm's law in order to calculate my current, where my current is given by V divided by this resistance value, or in this case is R. Okay, and if you do the math, put your voltage value at the numerator and divide it with your resistor value, you will find that your current is 1, the magnitude is 1, and the angle gives you the same angle you see at the voltage over here. So that's why it says here that the voltage and current are in phase with each other. Means that whatever value of angle for the current over here, for the voltage, is the same angle you see for the current. Same over here. And it is because of the element itself is just a resistor. If it is other than resistor, maybe the current will be a bit different. Okay, now why it is being like the current has the same angle, or the relationship of voltage and current behave like this? It is because the element that we have over here is resistor, where resistor, if you would like to write it in a complex form, it is given by R with the angle of 0 over here. So in other words, I would like to say that 10, maybe this should not be here. Okay, the magnitude should be 10. And the angle of resistor in this case is also 0. That's why 20 minus 0 is 20. You still get the same value of angle with respect to the voltage. So in other words, whatever angle of the current, if whatever angle of the voltage, if you have resistor in your circuit, only resistor, not if you have other elements, it cannot be like this. Only resistor in your circuit, the current, okay, the magnitude will be depend on whatever value of resistor. However, for the angle, it should be in phase, okay, in phase with the voltage angle. Vice versa lah. If you have current over here, you need to try to find what is the angle of voltage. It should be by rearranging this formula, just by rearranging this formula to find the voltage. However, what I would like to highlight here is that voltage and currents are in phase with each other. So the current, the angle of voltage and the angle of current should be in phase if you have only resistor in your circuit. If you have inductor, okay, inductor have a phase shift its voltage and current. The voltage leads the current by 90 degrees, or the current lags the voltage by 90 degrees. In other words, if you have circuit, for example, here we have voltage and you have inductor. Okay, let's say we have voltage equals to 10 with the angle of 0 degrees. 0 degrees. And the question is, what is the current? Okay. And you know that Ohm's law gives us that I equals to V over R. However, we don't have R over here, but please remember that the R, not necessarily value of R, is basically the unit that we care about. So now voltage unit is volts, R unit is ohm. Okay. If you try to apply Ohm's law in this kind of circuit, you need to make sure that this element should be in the unit of ohm as well. Okay. Maybe the conversion I will later describe it in next class. However, I just give a teaser on what you expect on next class. In this slide, what I try to emphasize is that for inductors, the voltage always lead the current by 90 degrees, or the current should always lag the voltage by 90 degrees. In other words, if this is not a good, maybe it's quite difficult to understand. Maybe I put it over here. Okay. All right. What I try to tell you here is that, let's say this is the argon diagram that we are considering. So let's say our voltage is 10 with the angle of 0 degrees. This here is our voltage. And it says the voltage lead the current by 90 degrees. Means that the current, okay, the current should be drawn here. Okay. Always. Okay. Based on this kind of graphical representation, we can say that V lead I, or we can also write it like this: I lag V, and both here lagging by 90 degrees. This is only applied when you have just inductor in your circuit, just like circuit drawn here. You only have inductor in your circuit. If you have like additional, for example, you have resistor here, it's not going to happen like this, because there always modification of angle over here. If you have only inductor in your circuit, so the angle will be always 90 degrees. Maybe later on, next class, I will explain you a bit more detail on how does this 90 degrees come across and so on. And also for the capacitor. And the capacitor is basically, if you look at the statement here, it says that voltage lags the current by 90 degrees. Current lead the voltage by 90 degrees. By right, if you have like this argon diagram, let's say we consider our voltage is V with the angle of 0 degrees, the reference, right? Okay. And it says the voltage lag the current by 90 degrees, and current lead the voltage by 90 degrees. Means the current factor should be up here. This is the 90 degrees difference between voltage and current. So, and this 90 degrees only applies if you have only capacitor in your circuit. If you have combination of capacitor, inductor, or resistor, it's not going to happen like this. It's not, you cannot say that voltage is like the current, lagging the current by 90 degrees. If you have, for example, if you have a resistor over here, if you have like resistor, additional resistor over here, maybe here we have inductor, okay, over here, and capacitor. You cannot say that voltage lag the current by 90 degrees as well. This voltage lag current and current lead voltage by 90 degrees only happen if you have only capacitor in your circuit, considering this one is an AC circuit. Okay, this is the relationship of voltage and current in summary. For element R, if you try to use Ohm's law, you can find current by using this relationship, I equals to V over R, or this is basically Ohm's law. And the Ohm's law for inductor is given by J omega Li. I didn't explain yet this part. We'll try to discuss on this part in next class, these two. It's very important. And maybe, in just the next few slides, maybe next class, I try to stop now because I think we have a few more slides we need to finish. But we still have time. Next Thursday, we can sit together, meet together again, and try to discuss the one that we left over here. However, for summary, for today's summary, basically for element L, the current will always lag the voltage by 90 degrees. If you have only C in your circuit or only capacitor in your circuit, the current always lead the voltage by 90 degrees. Okay, I think we're gonna end the session, but before we end, I just want to remind you guys about the class activity or homework. Maybe a few of the questions here you can always do it now because it's not that difficult. Maybe practice problem 9.9, you need to know the example. I need to show you the example first in order for you to answer these two practice problems. As a reflection, basically today we finished this part. We spent a lot of time explaining about this part. If I just skip this part, maybe we can finish it earlier. We can finish up until the last bit, example 9.9. We also tackle this part, relationship between voltage and current in AC circuit. We still didn't look yet on this part. Maybe on Thursday, we will discuss this one and also a little bit on circuit calculation or circuit analysis. Simple circuit analysis consists of R, L, RC, and also RLC. At the moment, we only have time to cater these 3 points, maybe later on. All right. As I mentioned earlier, next topic will be RLR RC circuit. We try to apply Kirchhoff law, Ohm's law first, and then Kirchhoff law. Maybe we're going to have a look at working example for AC circuit analysis. And with that, I think I would like to finish our session today. And hopefully the one that I explained to you guys, please remember, especially on the one involving phasor diagram, phasor representation. It's very, I think it's new for you guys. You need to have more practice in order for you to really master how to determine whether this is lagging, this is leading. That one is very crucial. Other than that, I think you can the content itself you already seen earlier in your mathematics course, maybe advanced mathematics earlier on, about the complex number, trigonometry. Maybe you need to just revise it back in order for you to refresh back your knowledge. But this lagging and leading stuff is, I think, is something new for you guys. So you need to have please read through the textbook. And also, if you have any question, you can always ask me, whether in our WhatsApp group or in e-learning. However, if you ask in e-learning, please mention to me because sometimes I miss that one. All right. Any questions so far? Abu Bakar, late today. Have you filled out the? Huh? Have you filled
Yes,
out?
sir.
Have you filled out the attendance form?
Yes.
Okay, good. Anyway, I think I'm gonna stop the class, the session now. We meet again on Thursday, and remember, please join Thursday session because this is very important session. I think in order for you guys to really can analyze AC circuit, simple AC circuit. From that, you can build your you can master how to analyze AC circuit. Hopefully, remember, Thursday class is very important. I really need you guys to be on the session on Thursday. All right. Hope to see you guys on Thursday. For your information, I still didn't finish marking your test, but based on current performance or current status, I think you have problems in on answering question number 2. Am I right? For question number 1, I think some of you guys really excel, and some of you guys are so, but still acceptable. But question number 2, a lot of you guys could not answer. Adam, just are you there, Adam, during the session from 9 a.m. or just came in? Anyway, we see again on Thursday. Please, for those who didn't um, fill out the attendance form, please fill out the attendance form. All right, see you guys on Thursday. Assalamualaikum. Bye bye.
Salam.
See you, sir.
Thank you, sir.
Tak bisa ku jelaskan betapa besarnya cinta ini. Jiwa dan raga melengkapi indahnya perjalanan ini. Apabila ku terjaga bertaut tepi yang menyakitkan, tangisan indah dan senyuman mentarikan terus menang.